So in this video we're going to sketch y equals x to the sine x. So before doing anything, I'm going to sketch the two graphs separately just to see the values that we're going to deal with. So that's y equals x, and then I'm going to sketch just one interval of sine x, and even on the negative side. Ooh, that's a bit more than one interval. There, not the best, but it works. Right, so that's pi, that's 2 pi, that's pi over 2, and that's our minus pi over 2 and negative pi. So I think we would have to consider 3 different areas in the graph. So let's say that's our final graph. So we have our graph. So we would have to consider 3 different spaces. One thing would be obviously what happens at the y-intercept. One thing would be how the graph behaves on the positive side, and the other thing would be how the graph behaves on the negative side. So let's deal with the y-intercept first. So we have y equals x to the sine x. So at every point where, so suppose for the y-intercept, x would have to be 0, which means 0 to the 0, which is not defined, but we know that anything that's raised to 0 is 1. Okay, and then this is kind of a similar case to if we had sine x over x, we would have 0 over 0, but then because it's a ratio, it would be 1, right? So the y-intercept would be at 1. Now, we know the sine x hits 0 at pi, 2 pi, at every multiple of pi, right? So if we have, suppose x equals pi, so let x equals pi. So we would have y equals pi to the sine pi, which would be just pi to the 0, which would be 1. So at every point, at every multiple of pi, our graph is going to touch y equals 1. So I'm going to draw y equals 1. And say that every multiple of pi, so for example that's pi, that's 2 pi, whatever, it's going to hit our y equals 1 graph. Okay, now, so that's our intercept sorted. Now for the positive side, we know that the sine x graph peaks at 1, and this happens when x is pi over 2. So y equals x sine x, x to the sine x. So at pi over 2, we would just get pi over 2 to the sine pi over 2, which is 1. So we would just get y equals x. And this would repeat at every peak, right? So this means that if I drew a separate y equals x graph, say over there, suppose it just goes through the middle. If we drew this graph, every peak of the graph would be on the y equals x line. I haven't sketched this properly, so I'm going to fix this. Say it's this. That seems more reasonable. So every peak of our sine graph is going to be on this line. So there, it would be somewhere like on the top there. So it's going to go to infinity, and we would have our peaks on this line. Now our minima of the sine graph happens at 3 pi over 2. So at this point, we would have y equals 3 pi over 2 to the minus 1, which means we're essentially dealing with y equals 1 over x at every point where sine x gives minus 1. So if I draw a 1 over x graph, which looks something like this, I can say that all my minima are going to lie on this line. So our graph is going to behave something like this, and then it's going to meet somewhere along this line, so something like this, and it's going to come down. Obviously I've squished it a bit. It's going to meet there, and then it's going to touch this line. So that's what our graph is going to look like on the positive side. Now, thinking of the negative, there's really two ways we can deal with the negative. So it turns out that the graph is not defined for a negative x. Okay, so we said that's x equals 0. This is x is greater than 0. And for x is less than 0, the graph is not defined. Now, why does this happen? So let's see two things. We know the sine of minus pi over 6 would give us minus a half. Right, that's simple. If I sub this in, so I get y equals minus pi over 6 to the minus a half, because sine minus pi over 6 minus a half. I'm basically doing 1 over minus pi over 6 square rooted, right? But I can't square root a negative number, which means that this would give me an imaginary value. So this is one way of showing that this graph won't work in the negative side. And another thing with any exponential, which should be true, is if we have y equals x to the sine x, we should be able to say that y equals e to the ln of x to the sine x, which is e to the sine x times ln of x. And natural log of x is only defined for x is greater than 0. So our domain is only x is greater than 0, and the graph is not defined for a negative x. So this is what the graph looks like finally.